Imagine that our perception of the universe is limited by its age, and the time it takes for light to travel to Earth. This conceals its true magnificence from us. What we see as the edge of our universe is not actually its end. Most scientists agree that beyond our observable horizon, there is more space that we have yet to see. We will delve into the darkness of unknown territories, disregarding concepts like redshift and light delay, to finally understand the nature of the cosmos beyond our observable universe. Any observer in the universe sees the cosmos ending at this horizon, beyond which light from distant galaxies hasn't had enough time to reach us in the 13.8 billion years since the universe's birth. Therefore, our optical view of the cosmos fades into an all-encompassing curtain of darkness that conceals the observable universe. But this curtain is not the true edge of our universe. In the radio spectrum, we find the cosmic microwave background, ubiquitous relic radiation left over from the Big Bang. This background is the oldest and most complete detected light signal in the universe, allowing us to estimate the properties of the space that may lie beyond our observable universe. On the largest cosmic scales, the universe appears remarkably uniform and isotropic, with matter evenly distributed with only local deviations. Therefore, beyond the cosmic horizon, we expect to find similar structures, clusters of galaxies and voids forming a cosmic web. The absence of light delay would allow us to see a much larger and more developed cosmos, expanding more than 100 billion light-years. The farthest galaxies, such as GNZ11, HD1, and Glass Z13, currently located at depths of over 33 billion light-years, would no longer appear as primordial star and gas clusters. They would likely resemble galaxies in our local volume, like the Milky Way, Andromeda, or giant elliptical galaxies like Messier 87. The question of what lies beyond our observable universe is relatively simple to answer. More cosmos with similar structures. But the more challenging question is, how much more is out there? To answer this, we need to understand the shape of the universe as a whole. In ancient times, people believed the universe was spherical, with Earth at the center, surrounded by physical boundaries. However, today we know that we see no signs of such boundaries. Scientists believe that the universe likely has no physical edge, but rather resembles the surface of a sphere, which is finite but without borders. The curvature of space is related to the energy density of the universe, and this parameter can tell us about its global shape, size, and even possible fate. A gravity-dominated universe would have positive curvature, enclosing its volume like a sphere. Such a universe could slow, but in 1997 it became clear that the expansion of the universe is accelerating thanks to observations from the Hubble telescope. This means that the universe is not dominated by gravity, but is expanding under the influence of dark energy, a mysterious anti-gravity force that smooths out and inverts space. So continue exploring with us, as scientific discoveries constantly change our understanding of the cosmos. Who knows what other fascinating secrets await us in the boundless universe? Imagine a universe that continually expands, never stopping or reversing. This could occur in a cosmos with negative curvature, where gravity isn't strong enough to halt the expansion. Such a universe might have a strange shape like a saddle, a funnel, or even a horn, and it could be either finite or infinite. In this case, two parallel photons of light would soon diverge, flying into eternity, creating new space forever. Now imagine a universe at critical density, where omega equals 1, approximately 5.7 hydrogen atoms per cubic meter of space. Here, gravity and dark energy are perfectly balanced, creating no significant global curvature, and the universe has a flat geometry. In such a flat universe, which we expect to find if it is indeed infinite, two parallel lines would remain parallel forever. This universe would continue expanding endlessly, like an infinite sheet of cosmic paper. Therefore, we have three possible options: a universe with positive curvature, closing in on itself, a negatively curved universe expanding forever, and a flat universe balanced on the edge between them. But how can we determine the curvature of the universe? Scientists have two main methods. The first is to calculate the total energy density in the universe by observing its large-scale properties. In the 1960s, the discovery of the nearly homogeneous microwave background suggested that the universe has critical density. And in 1997, the discovery of cosmic acceleration indicated that space is either negatively curved or very close to flat. The second, more precise method involves studying the edge of our observable universe, the cosmic microwave background. This radiation, left over from the Big Bang, is a sort of snapshot of the entire observable universe when it was only 379,000 years old. If curvature exists, it is likely to be detected here. The cosmic microwave background is extremely uniform with only minor local fluctuations in average temperature. These fluctuations are mostly caused by density gradients in the early universe. By measuring the angular sizes and distances between hotspots, we can find signs of lensing that causes apparent distortions in the radiation. Scientists can draw triangles by measuring their internal angles to determine the curvature of the universe. In a spherically curved universe, these angles would sum to more than 180 degrees, like on the surface of the Earth. In a saddle-shaped universe, they would sum to less than 180 degrees. And in a flat infinite universe, the angles would sum to exactly 180 degrees. Using this method, the boomerang experiment was the first to map the cosmic microwave background anisotropy in detail, concluding that omega equals 1 with only a 10% margin of error. This further confirms suspicions that the universe might be flat. So, as we journey through the cosmos, we continuously uncover new mysteries. Who knows what other incredible discoveries await us in the boundless universe? Imagine a universe that continuously expands and remains uniquely balanced. This has been confirmed by various studies, including data from the Wilkinson Microwave Anisotropy Probe, which showed that the universe is predominantly flat and has a critical density. Further data from the European Space Agency's Planck satellite confirmed these findings with even greater precision. These discoveries have raised a new question in cosmology. Why is the universe so perfectly balanced at this boundary? There are three possible explanations for this phenomenon. First, the universe is indeed flat and likely infinite. This means the universe extends endlessly in all directions. Imagine an infinite sheet of paper that never ends. Second, the universe may be curved, but on such a large scale that we cannot detect it. And third, the topology of the universe might be so complex that it hides its true shape. The first hypothesis of an infinite universe raises intriguing questions. How could the universe reach infinity in a finite time if it began with the Big Bang? The Planck satellite also found strange uniformity on scales greater than 60 degrees, suggesting a finite universe. This is one of the main arguments for a finite universe. If the universe is indeed flat, it may have a complex topology that hides its true size. One popular example is a toroidal universe shaped like a donut. Imagine a sheet of paper rolled into a cylinder and then bent again so that the ends of the cylinder meet. In such a universe, if you travel in one direction, you would eventually return to your starting point, like in the game Pac-Man. This model explains why the cosmic microwave background looks the same in all directions. If the universe indeed has this shape, we would expect to see repeating patterns in the background radiation, but so far no such sequences have been detected. However, if the toroidal universe is larger than our observable universe, these repeating patterns might simply be beyond our field of view. Therefore, we have several exciting possibilities for explaining the shape and size of the universe. Despite our achievements, the cosmos continues to remain mysterious and open to new discoveries. Who knows what other secrets this infinite space holds? Imagine our universe expanding in a unique way, following the geometry of a torus, like a giant cosmic donut. Space-time flows through this torus like a river, expanding from the past horizon, the moment of the Big Bang, and then contracting towards the future horizon. When the universe begins to contract, it returns to its initial state, and then a new cycle, a new Big Bang begins. If this is the case, then our universe may be just one of many in an infinite cycle of birth, expansion, and contraction. But there are other possibilities. It could be that the universe has curvature we cannot measure from within our limited field of view. If it is positively curved, like a sphere, its dimensions are so vast that we cannot detect this curvature. And if it is negatively curved, it is even larger due to its rapid expansion. Either way, it becomes challenging to understand how the universe became so vast in 13.8 billion years. The Big Bang, as we usually imagine it as a small singularity, could not explain such a perfect balance of the universe. We would expect to see magnetic monopoles, temperature contrasts, and curvature. But we don't. The cosmic microwave background is so smooth and even that scientists pondered the physical reasons for this phenomenon. Thus, the theory of cosmic inflation emerged, developed by MIT physicist Alan Guth in the 1970s-80s. It explains that the universe expanded extremely rapidly for a very short time after the Big Bang. This expansion was so rapid that it made the curvature of the universe indistinguishable from flatness within our observable universe. Inflation also explains why the universe is so smooth and homogeneous. During this expansion, microscopic quantum fluctuations grew to macroscopic sizes, creating the density variations we observe today in the cosmic microwave background. It also explains why we see no significant deviations in space curvature. Interestingly, this theory of inflation is also related to dark energy, which continues to expand the universe today. It reminds us that our universe has a natural tendency to expand against all expectations. As one of the discoverers of dark energy, Dr. Adam Rees said, "Perhaps the universe does this from time to time." Thus, we have a fascinating explanation of our universe, which might be an infinite cycle or so vast that we cannot grasp its true dimensions. Despite our achievements, the cosmos remains mysterious and full of secrets, waiting for new discoveries.